So, ideal transducers. We've thus far been discussing mostly one-port elements of electronic systems, mechanical systems, and, well, mechanical, translational, and rotational systems. Remember back in electronics, the electronics part though, we did talk about a couple two-port, well actually even one was like 3 or 4 port, forget, element. I think it was the op amp, it's I think 4 ports. But we did talk about a very specific two-port electronic element. Do you remember what it is? So a two-port element has this form. Draw a little diagram. Well, it doesn't need to be that big. I feel like I'm going to make it smaller. Okay, so on one side you have a port is comprised of 2 terminals, right? So you have a terminal on one side, a terminal on the other side, and one side has through variable F1 and a cross variable V1. The other side has through variable F2 and a cross variable V2. Generalized through and across variables there. So we had a very specific electronic two-port element that looked like this. Do you remember what it was? What was in the box?
Transformer.
Transformer, yeah. They were just, in the box were just 2 coils, right? They just interacted. Very poor representation of coils. That is a really effed up coil right there. It's bad news. If that is your coil, you probably should try again. Okay. So, so these two-port systems can model transducers, okay? And a transducer is an element that transfers energy between 2 energy domains or changes its form within an energy domain. So it could take maybe electronic energy and make it mechanical energy. So maybe mechanical rotational energy. You could take electronic energy and make it into mechanical translational energy. You could take mechanical translational energy and make it rotational energy. You could take mechanical rotational energy and make it into electronic energy. Of course, there are other energy domains, but those are the 3 that we've considered are the mechanical, rotational, translational, and then electronic system energy domains. So those are the 3 that we're thinking about converting between. Also, you can change its form within an energy domain. So we'll consider one example of that today, and that would be the gear. So you can trade off power flow variables using a transformer too, or a transducer as well. So the quintessential example of a transducer, which we will consider in detail more in later lectures, but a little bit today, is the motor, which converts electric energy to mechanical energy. However, many other system elements can be considered transducers, and we'll consider a few in this lecture. Each of the 2 ports has a through and an across variable, like we drew in the little figure there. We use the convention that the power into each port, P1 and P2, is positive, which has implications for the signs of the power flow variables F1, F2, V1, and V2. For A, because English, 2-port element, to transfer power and to not violate our assumption of power conservation, power 1 plus power 2 has to equal 0. Which implies that F1 V1 plus F2 V2 equals 0, which implies that F1 V1 equals negative F2 V2. Okay. Now this implies two different. So you could write two. Well, you could write more than that, but you could write two different expressions for this, and I'll tell you why we do it these two different ways in a moment. But here are the two. So we could get V1 over V2 on one side of the equation, and then divide through by V2 and divide through by F1, and you get that V1 over V2 equals negative F2 over F1. Or we could write, we could solve for essentially V1 over F2, I guess. V1 over F2, which equals, that's dividing through by F2 and then dividing through by F1, which gives us negative so negative V2 divided by F1. So those are our two expressions that we could write. We define, the reason that we wrote these is we're going to define these ratios. So we define the transformer ratio to be V1 over V2, which according to this expression here is equal to negative F2 over F1. So that's what we call the transformer ratio. Furthermore, we define the gyrator modulus, GY, to be V1 over F2, which is, according to this expression, negative V2 over F1. So those are our, the ratio and the modulus. So typically a ratio is what you have when you have two quantities with the same physical unit in a division, and if you have the quotient of two quantities that have different physical units, then that's more often called a modulus. Although people aren't super strict with that. The light's just blinking, isn't it? If we go crazy, that's why. So, for an ideal transducer, one that is linear, time invariant, and without power loss, we have only two non-trivial solutions that we can write. So there are two distinct solutions. One of them is this left-hand side grouping, or the other one is this right-hand side grouping. So either the across variables are related, or the through variables are related. And the through variables are related, or the across variable is related to the through variable, and the through variable is related to the across variable. So either the cross variables on each side are directly related, and the through variables on each side are directly related, or the across variable on one side is related to the through variable on the other side. and vice versa. So those are our two possibilities. In order to determine which is the case for a given element that you're trying to model as a two-port element, you have to know something about the physics of what's going on. Either you can come up with an analytic expression for a one variable on one side related to a variable on the other side, based on your understanding of the physics, or you just measured stuff and you're like, how, if I change the variable on this side, how does it change the variable on the other side? What depends on what? So you could do that too. Often we have a pretty decent idea from the physical insights that we have into the situation what it's going to be. So if you have a relationship where the across variables are related and the through variables are related, then this is a good model for your element, and so you could use what's called the transformer model, which is the left-hand side. This is the transformer model with the transformer ratio in it. And if instead your across variable on one side is related to the through variable on the other side, and the through variable on the first side is related to the cross variable on the other side, then you are better off using the gyrator model, which is a model of that case. Okay? Yeah?
So I didn't what does it mean, gyrator model? What do you mean by that?
I guess I essentially just mean exactly that these two equations are approximately true for your system. And for a transformer, so what we mean by those words is that the physics of that element work like this. If so, we call it a transformer. If the physics work like this, we call it a gyrator. So there's really no like deeper definition than just that. The sort of significance of the terms that we use. One way to get a handle on it is that transformers are coincident, fortunately. So an electronic transformer, like we drew that little like with the coils in there, an electrical transformer is a transformer. It follows a transformer model. Okay. Thank God. Otherwise, that would be confusing, right? And the gyrator is actually, it's too bad because electromechanical systems, I couldn't think of a single gyrator model. I couldn't think of a single element that behaves as a gyrator for electromechanical systems. If we include fluid systems, there's a really good example. The piston cylinder goes from a pressure, which is an across variable for a fluid system, to a force, which is a through variable for a translational mechanical system. So you have a gyrator. So the piston cylinder is a gyrator. We don't encounter, I couldn't think of one for an electromechanical system, but unfortunately. Maybe one day, maybe one of you guys will invent something that is that, and then I'll be able to use it as an example in class. So. Okay. Good. So that's what we mean by a transformer or a gyrator. So let's do a couple examples. And these examples should give us the, I guess like a grasp on like how we would come up with a model for these systems. And I realized that we spent a lot of time like actually using the equations and applying them to problems. And so I'm kind of trying to slow down in this lecture and start to talk about like, okay, say you have some physical system and you were trying to model it as a two-port element. How would you go about doing that? If it's in the book, that's great. The book actually has a lot of examples of different physical systems modeled in these different ways. And I think it's a great resource. And a little side note on that. The Rowell and Wormley text is, I think it's almost 20 years old now. There's still, I don't know about within the last couple years, but within the last few years though, the material, so they teach at MIT, the material from their course, I think it's Rowell's course, at MIT, it keeps getting updated. So it looks exactly like the textbook, but the PDF files are on the internet, and it's like when I search for some of these terms occasionally, I'll see one of them pop up. And he's updating and expanding some of the material in there, so there are some cool PDFs with even more examples worked out in the same way that the text works it out. So you might check that out. So yeah, this is this example though is sort of the quintessential one, right? A DC motor as the heart of what we're going for here is being able to model electromechanical systems that use DC motors and stuff. So we'll start talking about DC motors today. We'll continue talking about them probably, I guess, after Thanksgiving. So consider a DC motor. Okay, roughly speaking, how a DC motor works. We're going to use these terms, and I got to kind of give you guys, we'll go into more detail soon, but roughly speaking, a DC motor has well, whoa. I'll draw down here. A DC motor has a circuit that's connected to it, and then you go in here with the wires. The wire leads come in, and they are wound in a coil, which I'm gonna just do rectangularly because otherwise it's hard to follow it. And it could go around several loops. And it's connected to this is what's called the rotor, and the rotor is the thing that actually spins. So it's connected to a shaft that comes out. And then you have out here a either permanent magnets or another electromagnetic field. So I'll just write magnets out here, and this is sometimes called so I'll fix this. It's called the stator. Okay, this is the part of the motor, the housing that doesn't turn. So the rotor is in here. It's got those coils. If you run current through a wire, you guys might be familiar with the fact that a magnetic field is generated around the wire. And it interacts with the field that is going, say, between these two sides of the magnet. And using the right-hand rule and the physics that you learned in, I guess, physics 2, is it? Physics 3? Physics 2. Physics 3 is optics and stuff. It's 2, electronics. You have a force that's generated, so say out of the board coming at us, which I'll depict with this arrow there, and it wants to then turn the rotor. So you run current through the wire, it interacts with the magnetic field from the magnets of the stator, and then it wants to turn the rotor. And if you have several coils on your rotor, several magnets in your stator that are oriented around, you can keep this process going where it's always pushing you in one direction around the circuit. And you have to have either brushes or some other commutator. We'll talk more about that later to reverse the direction of the field of the current flowing. But in any case, the result is that we get this torque that occurs on eventually the shaft, right? Coming out of the motor, so you apply current to it, you get this rotation of your shaft on the outside. And we're going to talk about it broadly in terms of the rotor radius. So R is going to be that, rotor radius. The number of coil turns, N, so I just drew 2 turns, like it goes around once and it goes around another time, so that's 2 turns. But clearly you want to have more turns because how it shows up in the formula, the more turns, the better. So you want lots of turns. And then background field B is, so I'll switch colors for just a moment.
Just a quick interrupt.
Yeah, what's up?
So, in the electrical motor, there are also wires that are turning, like they're in coils. I mean, just like a transformer.
Yeah, so they're coiled as well, and that's to produce a magnetic field that's stronger in a certain direction. So you coil it more and more times, and you get a stronger interaction.
And that will give you like a higher torque in the long run.
Yeah, and actually that's the formula we're about to write down,
Oh,
or
okay.
that we're going to see here, which says that if you have more turns, so you run, say, 1 amp through this, that's I.
Mhm.
If you have 10 turns, you get a factor of 10 multiplying I, giving you torque.
Yeah.
If you have 100 turns, you have a factor of 100 multiplying I to give you torque. So the more turns, the more torque. Of course, geometrically, you can only fit so many. And you can fit more with a smaller diameter wire, but then you have current. I mean, you can't run
That's high.
as much current through a smaller wire. So you've got that sort of trade-off. So designing motors is a really, I mean, people still come out with new motor designs all the time, and they like try to make them a little bit more efficient, a little bit higher torque, and all that. And it depends also the performance that you care about is different for different applications. So they make some motors that are going to be like really good at performing at like high torque and low speed, but other ones that are going to be really efficient at high speed. So yeah, and we'll talk more about the different types of motors too. So DC motors are great, like sort of powerhouse. This is like the great heart of a lot of the electromechanical systems you can design. But more recently, there are some other types of motors that come out, like stepper motors, that are really useful for specific applications. So we'll talk about how those work too. So, yeah. So this is, and then there's this background magnetic field that's happening. That's the B field, background magnetic field for the magnets. And so the strength of that field also goes in. So the more background fields you have, the better. And then also, of course, the rotor length. So the length of the rotor is also a factor. So L. So those are all aspects of this relationship between the current on the electrical side, I, and the torque on the rotational mechanical side. So what we're going to do, so I give you this, and this is something that you can sort of derive it from a simple physical model of a motor, just like we drew. So we want to determine the DC motor, if DC motors are transformers or gyrators first. Then we'll find the transformer or gyrator, so the transformer ratio or the gyrator modulus. And then we'll derive the relation between the voltage and the angular velocity, assuming that it is an ideal transducer. So we're given this relationship between three variables. We should, if we assume it's an ideal transducer, we should be able to derive the relationship between the cross variables. So how are we going to decide if it's a transformer or a gyrator? Right. So what do we're given one of them, right? we're gonna have to find the other, but we can actually figure it out from just one equation, can't we? So what is this, an across or a through? Through, torque's through, and is current across or through? Through. So they're both through, therefore we have an equation that looks like this equation, right? It relates through variable on one side to the through variable on the other side. And so for an electromechanical system that has a source on the electronic side, so a motor is going to have a source on the electronic side, and it's going to have the load on the mechanical side. Usually we call the source side 1 and the load side 2. That's the direction that power's flowing. So we've got our through variable 1 being the current, right? And our through variable 2 being the torque. So we have torque equals negative TF times I. So from the TF equations, we know that torque is equal to negative TF times I. This matches what I'll star this equation. This matches star. Matches the equation that was given. The torque is proportional to the current. So therefore, a DC motor is a transformer. The second step is to find what we're going to choose to find the transformer ratio, because it's a transformer, not the gyrator modulus. So step 2 is to find the transformer ratio. And we actually kind of got partway there in this last part, right? We know that T is equal to negative TFI. We could actually just immediately look and identify if we wanted to, but also we could say, well, we know that TF is going to be equal to negative T over I, and we could solve for negative T over I in this equation. Either one, I'm fine with either. So let's do that. Let's say, okay, from this we know that TF equals negative T over I, which if we solving for this, for this in the star equation, we get, in the star equation, T over I is just equal to negative 2R NBL, right? So negative T over I is just 2R NBL. So negative T over I equals 2 NBL, 2 NBL. Yeah. There should be an R in this equation, y'all. Yeah, there is. I just didn't see it. There we go. So now we're good. So what is our TF? To RNBL. not too shabby. So then our third question is to derive the relationship between the voltage across the motor on the electronic side and the angular velocity on the other side. So if it's a transformer, then that there must be a relationship there, under the assumption that it is an ideal transducer. And motors it's pretty well modeled by that, and we'll talk a little bit more about the DC motor model we'll use. So if I come back over here, this is the equation that we've worked with, right? This one right here. This other one must be true if it's a transformer, right? So this is the relationship between the two across variables. We know that V2 equals V1 over TF. We just need to identify what V1, V2 are. We already have TF, so pretty much done. I'll just write from the TF model. So what is our across variable on the output side, on the 2 side?
Omega.
Omega, yeah, right? Because it's the side that has the it's where the load is. It's the mechanical side. Then we have on the electronic side, the input side. What's the across variable?
Voltage.
Voltage. So divided by TF, which is just V over 2R and BL. And that is the relationship. So let's think about this a minute. And we're going to keep talking about it, but it's good to have multiple conversations about motors. So the current and the torque are proportional, and the angular velocity and the voltage are proportional. And remember that the power is the product. The power on one side is the product of the current and the voltage. Power on the other side is the product of the torque and the angular velocity. So often what we think about with motors is we are trading off in different operating regimes between torque and angular velocity and current and voltage. Those are the things that we're playing with. Now, there are certain situations that have significant implications, and one of them, and we'll consider more, but one of them is when the angular velocity is 0, which is to say when the angular velocity has been stopped and you've got a shaft that's not moving, right? So maybe your load got stuck or whatever it is. Maybe you're trying to lift something using a motor and you can't lift it. You're just trying as much as you can. If you've got constant power, say if your power isn't changing, then as your omega goes down, your voltage goes down. If you're still delivering that power, you've got to increase your current more and more and more, and that's what happens. You start pulling more and more current, it's good because the torque goes up, right? But as the torque goes up and the current goes up, if you remain stuck and you don't get going, the current draw gets significant. And again, it gets hot because there is some resistance in the motor. So the coils have some resistance. And if you start flowing more and more current through them, you get more and more resistive heating, right? And that heat can actually cause damage to the motor, can essentially melt stuff.
Yeah.
You don't want to do that. Melting stuff is almost never what you want. Unless it's cheese, then it's good. So you don't want to melt your motor. Some motors can handle. So really, it's not just a motor thing. Because if you draw, so you could have a motor that's got like really nice, thick wires in there, and maybe some really good heat sinking out of the chassis. But if you run enough current, you can put too much current into any motor. So it's not just your motor you have to think about. It's how much power you can supply, what situations you might run into where you have a stall, and how long you can be in that stall. Because heat is something that dissipates, but it dissipates, slowly. So you can often get away with running full currents for a short period of time, but you got to know how much time that's okay, and that's one of the things that I really like about this is that you can start answering questions like, how long can I run at stall before my temperature gets too high in my motor? You can start answering questions like that, which is really, really cool. A lot of times it's difficult to answer those questions without a good dynamic model. You can answer questions like, well, I know that if I can't run it for, indefinitely, but you don't know how long you can run it. So dynamic model helps answer the questions about like how long you can run it. Okay, cool. So this is the DC motor. We're going to come back and then do another pass on the DC motor after Thanksgiving. But let's consider another type of transducer before we finish up today, and that's gears. So consider two gears with radii R1 and R2 and number of teeth N1 and N2. And I know you guys haven't taken machine design yet. That's next semester. So you guys are going to talk a lot more about gears, and there's a lot to gears to discuss. Like way more than you would think. So there's a lot. The gears are really, really cool and very complex, actually. However, we can model them for a dynamic system model pretty well as a transducer. So when you have a gear, you're thinking, it's a rotational mechanical system, right? So if two gears together, it's a rotational mechanical system. You're trading off what and what? What are the things you trade off with a gear?
Angular velocity and torque.
Angular velocity and torque, right? So you can have, so when you, for instance, we'll talk more about this, but a lot of DC a lot of motors are more efficient when you run them at high speed, okay? And also, a lot of applications require something to move at low speed. So, and also at a lot of motors don't have a lot of torque. Those are sort of low-end torque that you really need. You need that torque sometimes to be higher than it is. So you're willing to let your motor run at a high speed and have your load move at a lower speed to get some more torque to it, which is really common for a lot of automation things. You have a motor that is better to run higher speed, but you got to gear it down so that it moves the load at a lower speed. So, for instance, you're going to run a motor at like 1,000 RPM. Yeah, like 1,000 RPM. You don't necessarily want your load to be spinning at 1,000 RPM. And also, you probably want more torque out of it than you care about the speed. A lot of times the speed is not what you want. So, this gearing helps us do that. That's one of the things that gears are used for. But it's primarily, that's a lot of things use that concept. You're trading off torque and speed. So, consider two gears, radii R1 and R2, and number of teeth N1 and N2. We'll determine the power flow variables for the gears, and I think that we might have already done that. I heard that we're trading off torque and angular velocity. So those are our two power flow variables. And we're going to need to write two independent equations relating these power flow variables. Let's draw a little diagram. I think that drawing diagrams of this kind of helps. So let's look at a big gear and then an idler, a small gear. And they each are connected to a shaft, right? And the place where their radii meet, it's called the effective radius, and there's a lot of terminology with gears, but we'll just sort of simplify all that, and we'll just say this is R1, this is R2, and their teeth meet right at that effective radius, let's say. And let's define the positive rotation direction for the angular velocity one and torque one, and the positive angular velocity 2 and torque 2. So, well, we're gonna use negative signs and whatever. So, yeah, I define them both so that the right-hand rule comes out of the board for both directions, and then we know if it's negative, then it's going into the board. But yes, you're right. They're clearly they're not both gonna be positive at the same time, because we're gonna make the assumption that there's no slipping happening here. Okay, if your gear is slipping, it's not working the way you intended. Okay, it's bad news if your gear is slipping. It probably means you broke teeth on it. So you have this is where we're going to get our two independent equations, which is part 2. Two independent equations relating to power flow variables. So the first thing that we notice, oh God, we're running late as always. It's okay. You guys still love me, right? Okay. So the at this point, as you guys already observed, the tangential velocity better match up, right? So for no slipping, tangential velocity should be equal. So
does that mean the between each gear has to be equal?
yeah, so that means, so I'll make a little larger diagram of just that interaction. So that means that right here, the velocity of both of them the tangential velocity should be equal.
But for some reason it just doesn't make sense in my brain. But so you're saying that because the big one is covering more ground, wouldn't the small one be going faster?
So rotationally, yes.
Okay.
But at that point, because we can't have any slipping between the two gears,
Yeah.
at that point they must be going at the same speed tangentially.
Yeah.
Rotationally, they're at different speeds, but tangentially they're the same. And that this is actually the constraint. And you could think of it also as like if you had two cylinders that had like rubber on the outside that were pressed against each other and they were turning and there was no slipping between them. At that point where they're meeting, they're not slipping, so they must be moving at the same velocity. It's sort of like rolling when you did dynamics problems when you had rolling. Like at the point of contact, that's the instantaneous center of zero velocity, right? So, yeah, rolling's always weird. Freaks everyone out. But, yeah, so we've got a tangential velocity there. If you wanted to write that tangential velocity in terms of R and R1 and omega 1, what would it be? R1 omega 1, right? That's the tangential velocity for the R1 gear, for gear 1. For gear 2, we have positive omega going the other way, so we actually have to put a negative sign out there. But it's R2, negative R2 omega 2. And that's where the negative sign came from. If we had gone with omega 1 and omega 2 going in opposite directions already, we wouldn't have a negative sign there. But this is where that gets compensated for. So we can solve for omega 1 over omega 2, which is equal to negative R2 over R1. Great. So we have one relationship. The other one's going to come from the fact that the tangential force must be equal, because tangential force must be equal because, why? Newton had a law about that.
Every action has
Equal
equal
and
and
opposite
opposite reaction.
Yeah, so the force that interacts is going to be the same for each of them. And so we could think of the force interaction as being met there. And that gives us so the tangential force for one of these is R1 T1. So they're opposite direction though, right? They're equal and opposite. That's what I should write. And opposite. So R1 T1 is going one direction. And actually R2 T2, the force that comes from multiplying the radius by the torque, is actually already headed in the opposite direction because of the way we put our signs together. So therefore R1 T1 equals R2 T2, and you can solve for the relationship that T1 over T2 equals R2 over R1. Great. So we're almost done. 3 was to say, is this a transformer or a gyrator? What do you guys think? Transformer, right? Because across to across and through to through. And then finally, step 4, find the transformer ratio or the gyrator modulus. Clearly we need to find the transformer ratio because it's a transformer. So we look up back. V1 over V2, the easiest one, I think, in this case is to use V1 over V2 because we already have that, which is omega 1 over omega 2 is equal to negative R2 over R1. So TF equals, so omega 1 over omega 2, right? Omega 1 over omega 2, which is equal to negative R2 over R1 from this expression. And that is our transformer ratio. Yeah?
Excuse me again. So why it's number 3 transformer?
It's because we looked at the two equations that we came up with. So we derived this equation and this equation, and they relate the two across variables directly and the two through variables directly. So if you look back over in the definition, a transformer is defined as being an element that relates the across variables directly and the through variables directly, whereas a gyrator would relate the across variable to the through variable. We didn't do an example of a gyrator because for electromechanical systems I couldn't come up with one.
Okay, yeah.
But this would be, so if we came up with an element that related directly the current to the voltage, or the current to the angular velocity, and the torque was related to the voltage, that would be an electronic or an electromechanical gyrator. But we didn't have that in this case. We had an across variable related to an across variable, and the same with this case, a cross variable related to a cross variable, and therefore through variable related to through variable. Okay? All right. Any other questions? I know I kept you guys late. Yeah.
For this tangential force relation, shouldn't we write the force is equal to the torque divided by the radius? or
Yes. So I sort of skipped that step.
okay.
Right. So what you're right. The force. So you can say like the force tangential for R1. Let's say tangential 1 is equal to R1 T1,
Oh, yeah, yeah, yeah.
and force tangential 2 is equal to R2 T2, and then we should say, oh, these are equal to each other. And that's where I got it. So I skipped that step.
But you're multiplying the torque by radius. That's not.
Oh, yeah.
So a torque is in SI units a Newton meter, right?
Okay.
You multiply that by a radius,
Yeah.
you will get a Newton, so you get force. Hey, all right. I should probably stop recording. Sensitive.